My name is Les Brown. I'm a hydrogeologist and I'm representing the Speleological Union of Ireland. The presentation I'm going to give is on the understanding of Karst system of the Arney. The key points of my presentation are as following. The Arney catchment comprises, sorry, can I stop? I've a problem.
That's okay, no problem. Yeah, you can start again just from the top. Okay.
The key points of my presentation are as follows. Firstly, the River Arney catchment comprises of limestone and sandstone with shale lithologies, and these have contrasting runoff and recharge characteristics. Secondly, the limestone catchment includes extensive upland karst. Now, previous research has identified that the karst hydrogeology is complex and well-developed conduits form pathways through the limestone aquifer. And this study in particular focuses on proving connectivity between sinks and springs so that subcatchment boundaries can be refined and characterized. The focus of the work to date has been on the Rue subcatchment of the Arney River, and we'll be expanding in 2021 to the upper and lower Loch McNean area. To give you an insight into the setting of the Culp karst, I'm going to talk briefly about the geology, the hydrology, and the hydrogeology of the area. The Culp Mountain itself is a 5-kilometer long sandstone ridge, but the lower slopes are all limestone. And you can see some quite nice limestone pavement in this photograph here. The rainfall from the upper slopes forms rivers and streams that drain off those slopes and onto the lower slopes where they sink into caves and cave systems, emerging at the edge of the escarpment in springs. Looking at the geology, you can see the limestone area is characterized by the purple and the blue areas, and these are the lower slopes on the mountain. The upper slopes, as I mentioned, they're all sandstone and shale. And whilst all the rainfall runs off the sandstone and shale upper slopes, the lower slopes are where the rainfall directly recharges into the limestone. This is a generalized geology map of the Culp Mountain area, with the white area showing the limestone and the grey area showing the non-limestones. And on top of this, I've overlain the drainage systems, and you can see the caves that have been surveyed and mapped. These include some of the longest caves in Ireland, including Shannon Cave and Marble Arch Caves, Marble Arch and Cascade cave systems. Now, on the upper slopes, when those streams and rivers drain off the sandstones and onto limestone, they drop into a number of quite deep potholes and shafts. This one, it's about 20 meters deep. It's called Pigeon Pot. That photograph was taken in the summer, but in the winter time, there is a substantial stream going over the edge of the pothole and down into the cave. The cave systems tend to be quite extensive, branching tributary cave systems. This photograph of Shannon Cave shows a significant incising of the cave system over time, and you can see the streamway below the cave there. This particular passage is about 20 meters high and about 3 meters wide. And at the edge of the escarpment, we have risings. This is the Marble Arch rising, which is the largest rising in the Culp karst. The water rising at from this cave system goes to the Cladach Glen, which goes down to the Arney River. This is one of the largest springs that go into the Arney River. Now, we've been mapping out the flow paths of the groundwater as it goes through the Karst aquifer using fluorescent dyes. And as part of this project, 2 logging submersible fluorometers were purchased. And these enabled us to place the loggers in the springs so that we could leave them logging for between 6 to 8 weeks, taking a water reading every 10 minutes and logging for the fluorescence of 3 particular dyes that we're using on this project. 3 dyes we were using were fluorescein, rhodamine WT, and optical brightening agent. At the 2 springs in question, we installed temporary casings into the streamways so that we could put those fluorometers into the water and have them securely locked. Now, these casings have slots at the bottom of them, allowing the water to come in so that the water can be sampled by the fluorometers. And here's 2 slides of the main 2 dyes we were using, fluorescein, the green fluorescent dye, and rhodamine WT with its red color. Optical brightening agent is colorless, and we've been using that on occasion, but we found the optical brightening agent was providing not as clear results as rhodamine and fluorescein, so we relied mainly on fluorescein and rhodamine for this particular trace. This is an example of the results we got from the fluorometers. In this case, we were using fluorescein and rhodamine, and the fluorescein is shown in grey and green, and the rhodamine in red. You can see that we have a background level of fluorescence with the fluorescein and rhodamine. And you can see the large spikes when that pulse of dye came past the detector. Now, the baseline for fluorescein and rhodamine is due to the natural fluorescence of waters in the area, which is usually derived from organics in the peatlands that the main catchment lies in. But it was very important that we had loggers in the water to record baseline before the dye came through, so that we could determine what was a positive result and what was a fluctuating baseline. In this particular case, which was a trace from Pigeon Pot to Shannon Cave, we had 2 very clear positive results. The rhodamine breaking through after 3 days, 3 hours and 30 minutes, and the fluorescein breaking through after 1 hour and 55 minutes. Now, we use the data from the fluorometers to show where we have positive traces from sink to resurgent. This is a summary of the water tracing prior to the catchment care project. And as you can see, there was a significant amount of water tracing in the area. Most of this tracing was done manually. It was done by taking water samples, collecting water samples, and analyzing them in the lab. The benefit of the fluorometers that we're using, the submersible logging fluorometers that we're using for catchment care, it really speeds up the process. So it means we can carry out many more dye traces in a much shorter period of time. So this is the generalized lines which link sink to resurgence before catchment care. And we've added in multiple additional tracing lines now. And this has really enhanced our understanding of how the catchment divides are lying across the limestone area. In terms of the different colors of arrows that you're seeing on the map here, those arrows that are red drain to the Shannon River system. Those arrows that are light blue drain to the River Arney, and those that are dark blue are draining to the tributary to the Arney, the Rue. I've made the lines thicker where we have the more recent tracer tests. So the thicker lines here are traces that we've undertaken as part of catchment care. And we've really been focusing on the northwestern corner of this catchment map where we have Polnegossan Cave, because this is an area where we have a catchment divide between the River Shannon and the River Erne, where the Rue tributary to the Arney drains to the River Erne. So we have a catchment divide here between two quite sizable river drainage basins. So like I said, we're going to focus in a little bit now on the Polnegossan Cave area, which has been the focus of research over this last winter. If we look at Polnegossan Cave, it's a cave of 2.5 kilometers in length, and it has a stream that sinks into the entrance. Now, this stream has been proven to drain to Barron Rising, which is the main spring in the Rue catchment. So we know this is the source of at least part of the water that comes out of that spring that feeds into the Rue. There is a second streamway in the cave, though, and prior to the catchment care work, this second stream had never been traced. So one of the primary focuses we had of the project for the winter of 2020-2021 was to determine if this stream also drained to Barron Rising, or in fact, does it drain elsewhere, and do we have a catchment divide running through the cave? Now, we've proven that the additional stream, the stream in the southeastern corner, that drains to the Geelan Spring and the Shannon Pot Rising system. So it's part of the Shannon River system. And we've also proven where the water comes from. It comes from a small doe line, which is in the catchment of the cave. So we've added significant clarity to this particular cave system, and we can confirm that in these normal flow conditions, there are two completely different streamways in the cave, one draining to Barron Rising and one draining to the Shannon River. And this lets us draw a catchment divide between these two river systems on the map. So the catchment divide goes right through the middle of the cave. Now, in normal conditions, the central part of the cave system doesn't have a streamway in it, it's completely dry. That section of the cave is particularly muddy, and there had always been thought that the cave was particularly flood prone, with the cave being where the cave was flooding, mud was being deposited, being remobilized and deposited in the cave. So as part of the project, we were keen to see not just how the drainage operated under normal flow conditions, but we were very keen to see how the hydrology changed under storm conditions. So we had done tracing under normal flow conditions, and we'd proven that there was two separate drainage systems, one going to Barron and one going to Shannon. But we undertook further tests when it was in full flood, just after a large storm. So yes, we had proven that Polnegossan, under normal conditions, drains to the Barron Rising. But those tests that we undertook when the cave was in flood, when we had a big storm event, they actually showed that the water went both to Barron and to the River Shannon. So we have an example of water sinking and bifurcating, going to two separate springs, two completely separate river drainage basins. Now, this is a really good example of divergent flow, and it does occur in Karst quite regularly, and it occurs at times where there is significant backing up of water levels in the cave system and water overflows. Now, to go into a bit more detail about how this happens in Polnegossan Cave, we know that in normal flow, the surface water stream sinks into the cave and then rapidly is lost into the floor of waterfall chamber. but there's a throttle, there's a capacity on the amount of water that can sink into a waterfall chamber. And when storm events happen, the water level in that chamber starts to rise. And it rises to a certain point where it spills over into the rest of the cave, floods the remaining part of the cave, and the water overflows into that further streamway, the streamway that goes to Shannon Cave. So here we have an example of, in low flow, in normal flow, groundwater, the stream entering the cave drains to Barron, but the conditions in the cave change dramatically during storm events. The cave floods, the cave backs up, and it overflows to a separate catchment. And then as the groundwater levels in the cave start to recede, the cave switches back into just draining to Barron rising. So this is a phenomenon that only occurs during storm events. And during those storm events, the majority of the storm water flow, it goes to the Shannon pot system, it goes to the Shannon River. So there's ongoing research, this is work in progress, but the next stage is to work out what the capacity of that base flow is, and then we can identify the level at which water overflows and goes to Shannon River, but also how much water actually would overflow and go to the Shannon River. So on the back of this research, we can show that we've revised the boundary of the catchment between the River Erne, in particular the tributary of the Rue, the tributary of the Arney, and the River Shannon. But we've also shown that it's very complex and it changes. The groundwater divide changes depending on the conditions of the stream. So in high flow, the divide is different to when it is in low flow. So essentially, the flow in the aquifer becomes very complicated during those stormwater events. So a summary of the work we've done so far and a summary of the results. So we've undertaken a total of 26 trace tests during 2020 to 2021. These tests have been from several different sinks, and they've been with detection in 2 springs. 4 of the sinks that we have traced are completely new, they hadn't been traced previously. We've shown that tests from individual sinks have been repeated under different flows, and we've shown that the pathways differ depending on whether the flow is normal or whether the flow is in storm condition. We knew that there was already one divergent flow path in the Karst, and that was the Pigeon Pot stream. But this recent data with catchment care, we've now confirmed that there are an additional 3 sinks where we have divergent flow. Not just the Polney-Ossen stream, which I showed in the schematics earlier, but we have a similar situation with 2 other stream sinks in the area, one referred to as L6 and another one as Apol Neblinia. All 3 of these new sinks that are divergent are in the Rue catchment, and it could be a characteristic of the Rue subcatchment that we have this divergent flow during storm events. And as we said, as the flow diverges during storm events, it's a significant proportion of the storm water. In fact, it's probably the majority of the storm water that overflows. So during those big storm events, the majority of the storm flow goes to the River Shannon, with only a base flow component going to the Barron and the Rue tributary. The program is ongoing. As I mentioned, we're continuing research in Polney-Ossen Cave and the other 2 sinks that have divergent flow. We would like to be able to quantify what the base flow is, and we'd like to quantify at what level the overflow occurs. So there's ongoing research there, and that will be going on from autumn and winter 2021. At the moment, the groundwater levels have become very low, and they're going to the summer levels at the moment. So we don't have enough water in the cave systems to continue the trace tests over the summer. When we've finished with the work in the Polney-Ossen Cave area, we are also going to start looking at the southern shore of Upper Loch McNeil, where we have some new caves discovered. And we're also going to look at the northern shore of Lower Loch McNeil, which has quite complex hydrogeology. And we need to determine the sinks that feed the springs coming into the that northern shore as well. So there's a lot of work to get on with. As part of the project, there was an intention for community engagement, but COVID has caused us to reduce that substantially. So most of the work that's been done has been done by myself and Dr. John Kelly with the support of local caving clubs. So it's very much so being done on a local basis at the moment. We've been engaging with landowners, but we haven't been able to bring the community in. The intention is to provide information to the community so that they have a greater understanding of what happens to those sinks, and the streams that sink underground into the limestone aquifer. But what we have done is we've been videoing quite a bit of the research we've been doing, so on caving trips and during the tracer tests, to give people an idea of the work that's ongoing and the work that we're doing. And we've had one video of the tracer testing published on the Catchment Care YouTube website. And then also as part of the Northern Ireland Science Week, we prepared a short documentary of the work we were doing, just to give people an idea of just how complicated the groundwater is in karst aquifers. And those links are on the screen there. The Catchment Care video is about 10 minutes long, and the documentary we prepared for NI Science Week is about 40 minutes long. Okay, that's the end of the presentation. Thank you very much.